We ran into some last-minute technical difficulties here, so I'm going to have Shane actually be running the presentation remotely. So unfortunately, you're going to hear me say, next slide, please, probably about 29 times this afternoon. So if you can bear with us on that one, we'll get through everything. So good morning and good afternoon again. On behalf of Gentex Corporation, welcome. I am Dave Newhouse, as Michael said. I'm the Industry Affairs and Regulatory Compliance Engineer for Gentex, and I've been very fortunate to have worked for Gentex Corporation for the past 3 decades. In fact, next month is my official 31st anniversary with the company. So just a little background information about me, because everybody loves to talk about themselves. I am currently serving on 3 NFPA technical committees, NFPA 101, 5000, and NFPA 72. I'm also serving on 9 UL standards technical panels, as well as the joint NEMA UL harmonization committee. This past year, I joined the International Code Council working groups for both building as well as fire codes, the Building Code Action Committee, BCAC, and also the Fire Code Action Committee, FCAC. I've been serving on the Automatic Fire Alarm Association, AFAA, the board of directors since 2010, as the chair of research and co-chair of codes and standards, and was recently elected to the executive committee as the association's treasurer. I began all this exciting endeavor in industry affairs and codes and standards by joining the National Electrical Manufacturers Association, also known as NEMA, their section committee back in 2006, and have served in various roles, in leadership roles as chair of the research and publications, and was recently appointed to the second vice chair of the section. So that concludes today's presentation. Thanks for joining me. Just kidding. Okay, thank you all again for this opportunity. I greatly appreciate being able to speak to you this afternoon, and I sincerely hope that you'll find something of interest for this virtual presentation. So without further ado, let's get started. Today we're going to talk about the new requirements for UL 217 and 268, which are 2 Underwriters Laboratories product listing standards for smoke detection. Next slide, please. Fantastic. So this would be a great time to ask you all if you're very familiar with the difference between smoke alarms and smoke detectors. For those that may be unaware, they both have very unique differences in both design as well as installation applications. A smoke alarm is a self-contained alarm with an internal smoke sensor or sensors that will sound an alarm signal when it senses smoke. A smoke alarm is typically installed in residential occupancies, hotel rooms, dormitories, and sleeping areas. Now, a smoke detector will provide a signal to a control panel, which will activate an alarm through a notification appliance. Smoke detectors are typically installed in commercial building occupancies. Although smoke alarms and smoke detectors operate on very different principles and have separate listing standards, the new requirements that we're going to be speaking about today are the same for both smoke alarms as well as smoke detectors. Now, back in 2015, UL announced new requirements for the 8th edition of UL 217, which is the standard for smoke alarms, and the following year, they released the requirement for the 7th edition of UL 268, which is the standard for smoke detectors. Now, there are over 400 modifications from the 7th edition to the 8th edition of UL 217. However, today we're only going to focus on 3 of these new requirements: the flaming polyurethane smoke test, the smoldering polyurethane foam test, and the cooking nuisance smoke test. Consequently, both standards include identical performance requirements for flaming polyurethane, smoldering polyurethane, and the cooking nuisance smoke test. These technical changes to the smoke alarm and smoke detection listing standards were needed due to the rapid technological advancements in our industry, as well as other important life safety reasons we're going to be discussing later in this presentation. These significant changes to the compliance requirements were implemented to both mitigate nuisance alarms, as well as ensure detection and response to both flaming and smoldering polyurethane materials. You may already be aware that the 2 most common types of conventional single sensor smoke detection technologies, that have been prevalent in the industry since the early 70s have some significant limitations. The ionization technology, known for sensing fast flaming particles of combustion, do not always recognize smoldering polyurethane smoke signatures. And conversely, photoelectric detection, that's known for recognizing smoldering particulates and reducing unwanted alarms, is not as efficient at detecting fast flaming polyurethane. Now, the revised requirements will necessitate new smoke alarms and smoke detectors to differentiate between smoke from common nuisance sources, such as toast or other non-lethal sources, from actual life-threatening smoke from a fire. The revised editions of the UL standards and resulting smarter smoke alarms and smoke detectors are perhaps the most significant technological change that suppliers and facility managers have seen in recent times. Okay, next slide, please. Now we're going to begin with the importance of smoke detection. We can see that residential fire deaths have decreased almost in half from a little over 6,000 deaths in 1978 to 3,400 deaths in 2017. We can also see that non-residential fires, such as commercial office buildings and hospital fire deaths, have decreased over 6 times, from 640 deaths in 1977 to 105 deaths in 2017. Yet hotel and motel fire deaths have increased by approximately 33%, from 62 in 1980 to 80 in 2017. Now, when looking at these fatalities, it's important to keep in mind that the US population has increased about 46%, from 222 million people in 78 to about 325 million people in 2017. So as the population is exponentially increasing, fire deaths as a whole are significantly decreasing. This fact clearly demonstrates that the products used in our industry are definitely having a great impact on saving lives. So what can be done to continue this trend of mitigating fatalities from fires? Let's take a look at some of the factors that limit an occupant's ability to safely exit the dwelling or building during a fire. Now, escape time, which will vary from occupancy to occupancy, is measured using calculations called ASET, or Available Safe Egress Time, and RSET, which is Required Safe Egress Time. ASET and RSET are performance-based tools that evaluate both occupancies as well as smoke alarms and or fire detection systems. ASET is actually a measurement of time between the ignition of the fire and a completely untenable condition, and it's usually conducted with empirical data or fire modeling software. The typical factors used in determining the point at which untenable conditions happen are visibility, which is determined by how much smoke is obscuring the view to safely exit. Also heat, which is obviously the temperature preventing a safe exit, and the amount of carbon monoxide that's being produced by incomplete combustion and builds up into specific occupancy during fires. Now, the required safe egress time is measured from the time between the ignition of the fire and the time that's required for the occupant to safely evacuate the building. RSET is determined by the sum of the alarm time, which is the point at which the occupant becomes aware of the fire, plus the pre-movement time, which is the time between notification and the decision to actually begin evacuation. Pre-movement time includes time to investigate, to look around and see if there's actually a fire, some time to gather your belongings, grab your coat, grab your jacket, grab some shoes, and or possibly searching for family members or pets. Then by adding the movement time, which is comprised of the walking speed, the flow rates, having to open doors, climbing stairs, etc. So RSET is actually determined by adding the alarm time plus the pre-movement time plus the movement time. Now it's interesting to think about the fact that if the escape times are basically a factor of the building design and the flammability of the materials that are used to furnish the occupancy, then what are the most contributing factors that could also be improved to reduce the time needed to safely egress. I've actually listed two very important factors here on this slide that could be improved that may contribute to the limiting an occupant's ability to safely egress a burning building. The first is alarm activation time, and the second is waking effectiveness. Now, alarm activation time is the speed at which alarms and detectors react and respond to burning or smoldering particulates of a fire. Alarm activation time is the largest contributing factor of these new requirements we're going to discuss today. In addition to alarm activation time, waking effectiveness is the audible alarm signal and is also a very important factor. I'm sure everybody's heard about the 520 hertz low frequency requirements that are finding their way into the marketplace, as well as the codes. But that's a presentation for another day. We'll talk about that one next time. All right, Shane, next slide, please. So when looking at decreased escape times, we can see the window of ASET times in flaming fires has decreased from 17 minutes in 1975 to only 3 minutes in 2007. Now remember, ASET is the time from which the ignition of a fire to completely untenable conditions. This is now happening at a rate of approximately 3 minutes or even less. I got a really interesting video coming up in a few slides that's going to help demonstrate exactly what this ASET window and what it is and how it dramatically increases decreases rather, over the past years. All right, next slide, please. So incidentally, this is a picture of Shane's house. Looking at decreased escape times, there are several explanations that can be attributed to decreased escape times over the past 40 years. One of them is the average physical size of a new single-family dwelling has almost doubled from 1,660 square feet in '73 to about 2,565 square feet in 2018. Construction materials also play a critical role in the decreased escape times. Real wood lumber has been replaced with engineered wood and other synthetic materials. Next slide, please. Now, not only construction materials, but also home furnishing materials have transitioned from genuine real wood furniture and cotton materials used in bedding, sofas, and chairs to synthetic materials such as vinyls, plastic, microfibers, and polyurethane foams. The combustion behavior between synthetic and natural materials is extremely different. Synthetic materials ignite and burn much faster than natural materials used to 40 years ago. They also generate a much higher heat and smoke release rates than natural materials do. Next slide, please. Now, synthetic materials have caused more fire deaths in the past 25 years. Not only do they have a rapid burn rate, but they burn hotter and much faster than traditional materials. Synthetic materials reach flashover at a much faster rate than natural materials do. In conjunction with hotter and faster burn rates, the speed at which oxygen is depleted also increases. Synthetics produce a lot of heavy, dense smoke and toxic gases. Hydrogen cyanide and carbon monoxide are among these highly toxic gases. Both can be lethal if inhaled, and both are produced when synthetics such as polyurethane foam is ignited. So it's very important that smoke alarms and smoke detectors provide enough early warning to the occupants for significant and safe egress time. Next slide, please. Oh, great. Okay, here comes the video I was speaking about earlier. Now, in setting this up, this video was recorded at the UL facilities in Northbrook, Illinois, and it's called Comparison of Room Furnishings. And it demonstrates very clearly how the difference in building materials and home furnishings impact occupant egress in the time of a fire. Now, several years ago, the research team at UL at Northbrook conducted side-by-side simulating living room fires to compare legacy home furnishing materials to those that are manufactured today. They began by constructing two 12-foot by 12-foot rooms inside of the large-scale fire test and research facility. Now, the first room on the left was constructed with cement board, hardwood flooring, and was furnished with a sofa filled with cotton batting and solid wood table that simulates furnishings from 45 years ago. Now the room on the right was constructed with gypsum board and carpet, padding, and furnished with a sofa manufactured with polyurethane foam and engineered wood table to simulate furnishings that are manufactured today. Now let's see what happens when they're ignited. Incidentally, this video has been sped up significantly, so we won't have to wait very long to see the results. All right, Shane, could you start that one for me? Fantastic. So we can see the pillows are ignited in both of the rooms. And you can see that the flame is starting to begin to appear on the left side after about 30 seconds. Approximately 1 minute into the video, we can see a plume of black smoke beginning to build from the synthetic materials on the right side. Notice how quickly the fire on the synthetic side is advancing. By about the 2-minute mark, there's already heavy, dense smoke up on the ceiling, and by 2.5 minutes into the video, the fire has already spread to the carpet and drapes. Yet the fire on the natural room side is barely progressing at all. At the 3-minute mark, the room on the right is completely uninhabitable, and at approximately 3 minutes and 40 seconds, the room has reached complete flashover. Now the room with the natural furnishings continued to burn for another 25 minutes. And it finally reaches flashover at about the 29-minute and 25-second mark. So this video does a great job of representing the need for early alarm activation time and waking effectiveness and required safe egress time. So you can see the materials here have a dramatic effect from 40 years ago to what they are actually today. All right, next slide, please. Now, there are many variations of polyurethane and polyurethane foam. I'm going to provide a few examples of polyurethane and its wide variety of uses. Closed-cell flexible polyurethane foam is commonly used throughout residential and commercial occupancies in many different applications. It's used as cushioning material in upholstered furniture as well as sofas and chairs. It's also used as bedding mattresses, as padding underneath carpeting, and for support and comfort. So in addition to flexible polyurethane foam, rigid PU foam is also widely used in the same occupancies for energy efficient insulation. It's used inside walls as well as to insulate windows and doors. Rigid PU foam can assist in reducing energy costs in residential and commercial occupancies. In addition to insulation, rigid PU foam is also effective in reducing noise levels. Polyurethane is also used in coatings for products such as wood and concrete for both appearance as well as to increase the lifespan of these products. Polyurethane is used as adhesives and sealants for bonding and tight seals. TPU, or thermoplastic polyurethane, and RIM, reaction injection molding, provide many applications for automotive, construction, computers, wiring insulation, and appliances, and including products that are actually used in our life safety industry. Polyurethane can be manufactured into fine threads and spun into nylon to produce stretchable garments such as sportswear and spandex. Now take a quick minute wherever you are, look around the room or the office that you're in, and just understand all of the different polyurethane materials that are around us. You can see mouse pads and keyboards and water bottles, monitors, chairs, carpeting. We're all definitely surrounded by this material. It's all around us. All right, next slide, please. Now, why was polyurethane foam chosen as a representative material for these new requirements? After watching the video, we can certainly understand the importance of the availability of safe egress time. We also understand the important role of early alarm activation time and early notification that smoke detection provides. But that in and of itself isn't a complete answer. Detection responsiveness needed to be expanded to ensure smoke detection would be able to recognize and respond to all synthetic materials used in homes and commercial furnishings. In other words, if smoke detection can't recognize the smoke signature or particles of these synthetic materials, then it certainly cannot provide an early warning. So you all set out to expand the range of particles, sizes, and colors beyond those that are used in the previous editions of UL 217 and 268. Those being paper, smoldering wood, flaming wood, as well as flammable liquid materials. Flaming polyurethane foam produced the smallest particles of all the materials that were tested at approximately 0.05 microns. Now, just for reference, that's about 1,000 times smaller than a human hair. So these smoke particles are extremely small. The particles are black in color when PU foam is ignited. Also, PU foam has another very unique property when it's ignited. The solid material begins to melt and will actually transition back into a liquid state. This liquid state will reignite, emitting a different smoke signature that's similar to the flaming liquid tests that are used today. So when this material is burned, it actually provides two very unique particulates within one single flaming test. When polyurethane foam is smoldered, it produces a particle size of approximately 0.09 microns, and that's about double the size of the flaming foam. It also produces a brownish gray color similar to gray poupon when it's smoldered. So the last two reasons you all considered using polyurethane foam is the familiarity that they have with its use. PU foam has been used in ANSI UL 1638, which is the standard for residential sprinklers for many, many years. This standard uses two sections of PU foam combined with a wood crib to simulate furniture. Due to the rapid flame spread and heat flux, it's an excellent material to test the response times of residential sprinklers. PU foam is also used in the European standard EN54 for fire detection and fire alarm systems. That standard uses 3 pieces of 20 by 20 by 3/4 inch slices of foam to gauge the response times of initiation devices. So flaming PU foam has been used in the industry for many years as a method in which to test smoke alarms, smoke detectors, and sprinklers. All right, next slide, please. So now we know why the standards were needed, why these changes rather in the standards were needed. We also know why the different material was chosen for flaming and smoldering requirements. Let's take a look at the actual requirements now in 217 and 268. We'll begin by looking at the flaming polyurethane foam test found in ANSI 217, 8th edition, section 51.4, and ANSI 268, 7th edition, in section I2. Next slide, please. Now, section 51.4 of 217 requires an 80-20 blend of polypropylene oxide polyol and polyether flexible foam for the PU test. It's important to note that no colorants or flame retardants are added to the foam during the manufacturing process, as these additives will definitely affect the particulate size as well as the buildup of smoke during the flaming tests. The last time I gave this presentation, I had a great question from the audience. Why are the flame retardants not used in the manufacturing of polyurethane foam? Wouldn't it be safer for everyone if the polyurethane foam would actually not combust? Now, the answer is very interesting. PBDEs, which is a very carcinogenic flame retardant, was actually used in polyurethane foam production prior to 2005. However, studies found that the retardants would actually break down and leach out of the furniture and become airborne as dust and inhaled. So eventually, fire retardants were removed from the polyurethane foam following a ban on PBDEs in California soon after 2006. Okay, so back to our flaming polyurethane requirements. A 14.5 inch by 17 inch by 3 inch section of foam is used for the flaming test. It must be conditioned for 48 hours prior to the test in an ambient room temperature of about 73 degrees with a 50% humidity rating. Following the conditioning, the foam is placed on a foil-lined tray which sits on a non-combustible tile. A little bit of alcohol is added to the corner of the foam and is ignited remotely. The size of the foam section, the placement, and ignition can all be varied to produce a valid test. The smoke build rate must be in accordance with the beam and mixed smoke profiles, and all 5 smoke alarms must activate before the 5% obscuration limit is reached. Now, speaking of those 5, I got to back up just a little bit. We use, for the test itself at UL, They use 5 smoke alarms for the polyurethane flaming and smoldering tests, 3 of which are mounted on the ceiling and 1 are mounted on each one of the 2 walls. And again, it must activate on or before the 5% smoke obscuration limit is reached. All right, next slide, please. Now in the photo on the left, you can actually see the foam sample. The bottom is wrapped in foil and is placed in a tray. You can also see the remote igniter in the background. The photo on the right is showing the foam approximately 5 minutes into the test. And as you can see, it's fully engulfed. All right, next slide, please. So that brings us to the smoldering polyurethane foam test. Let's take a look at the actual requirements in 217 section 53 and 268 section Annex I3. Next slide, please. All right, section 53 of 217 contains the requirements for smoldering polyurethane foam. And as you can see, the specifications of the smoldering foam are the same as those for flaming. It's an 80-20 blend with no colorants or flame retardants. The physical size of the foam is a little bit bigger. It's now 4 inches instead of 3 inches for the flaming foam. The conditioning is also the same at 73 degrees at about 50% humidity for 48 hours. Now, when it comes to the actual method of smoldering this polyurethane foam, the standards give a few examples of how this can be accomplished with the use of either radiant heaters, hot plates, or cartridge heaters. But regardless of the method that's used to smolder the foam, the sample is not allowed to transition into flame during any part of the test. And again, the size of the foam sample, as well as the method used to smolder it, can all be varied as long as the build rate is kept within the smoke profile. Now, the smoke build rate must be in accordance with the beam and MIC smoke profiles. If the build rate happens to drift out of profile, or if the foam ignites, the test is stopped, the room is cleared of smoke, the air is recycled, and the test will be reconducted. Now, another criteria of acceptance is that all 5 of the smoke alarms must activate on or before 12% obscuration for smoldering. And again, the 3 on the ceiling and the 2 samples on 1 on each wall. All right, next slide, please. Excuse me, needed a drink here. Now, UL designed a very sophisticated piece of equipment using cartridge heaters, very complex software algorithms, and a feedback system that provides a very consistent and very robust and very repeatable test. It kind of reminds me of a giant toaster, as the foam sample itself is actually slid in from the top. Now, the photo on the right represents a radiant type heater. And again, both types, as well as a hot plate, are all acceptable, provided that the equipment can actually produce a build rate that will remain in profile. All right, next slide, please. Okay, so let's move forward and take a look at the 3rd new requirement of the smoke detection standards, which is cooking nuisance resistance. Now, why are requirements needed for resistance to common cooking nuisances? According to an NFPA study, cooking is the #1 source of all nuisance alarms. Up to 73% of all nuisance alarms are caused by cooking-related instances. I'm sure this has happened to almost all of us at one point in our lives. We drop a couple of slices of bread in the toaster, walk away, and the toaster hangs onto the bread just a little bit too long. And instead of enjoying some golden brown cinnamon toast, we're rewarded with 85 decibels of screaming smoke alarms. And of course, the natural reaction to all this is what? Yeah, remove the battery or disable the alarm. We all have the full intention of reinstalling the battery at a later time, but we get busy. We have to make more cinnamon toast, right? But the smoke alarm is now disabled and completely unable to operate. According to another NFPA study in fatal fires, which had smoke alarms present but were not operating, 46% had missing or disconnected batteries. Very common problem that we're seeing out there in the industry. Now, as we all realize, the more nuisance alarms that we're exposed to, the more we naturally become complacent and less adept to recognize the sound of an alarm as a possible hazard. Something similar to the sound of a car alarm. If you hear an alarm blaring in a driveway or a parking lot, you're more likely to believe it's more of an annoyance than an actual emergency. All right, next slide, please. So why was frozen hamburger chosen for the cooking nuisance resistance test? Now, back in August of 2015, you all released a research study called the Characterization of Smoke Alarm Nuisance Sources from Cooking Scenarios. Wow, that's a big one. Now, this research proved the background for the new cooking nuisance requirements. It provided all the information needed to be able to actually draft the copy of these new requirements. Now, this report set out to accomplish two things. Number one, to determine the best surrogate of all cooking nuisances. And number two, to provide the research needed for the UL 217 task group to actually draft the cooking nuisance resistance requirements. Now, this project began with a literature review of all previously published research, which assisted in narrowing down a large list of possible cooking nuisances. Everything from pizza, bagels, bacon, and cheese sandwiches were reduced to 3 possible candidates: toasting bread, pan frying, and broiling hamburger. Now, the characterization of smoke alarm nuisance sources research successfully determined that broiling frozen hamburger best represented all of the cooking materials that were tested. Excuse me. Now, hamburger produces small particles when it's initially broiled at approximately 0.01 microns, followed by larger particles as the sample is heated up to approximately 1 micron. Now, this combination would prove best to challenge all smoke alarm types: ionization, photoelectric, and combination photoion alarms. As the test procedure was refined, the results became more and more repeatable. All right, next slide, please. Now let's take a look at the actual requirements for cooking nuisance smoke resistance test found in ANSI 217, section 54, and also ANSI 268, Annex I-4. Next slide, please. Now, section 54 of 217 contains the requirements for cooking nuisance testing. As you can see, the specifications call for frozen hamburger. Specifically, a blend of 75% lean beef and 25% soot with an approximate size of 3/4 inch thick by 4 inch diameter. Now, these samples are to be conditioned from -20 to -25 C, which is about -4 to 13 degrees F, for a minimum of 72 hours prior to testing. The method used for generating the particulates for this media is an electric range with a broiling option. Similar to the PU foam, the hamburger cannot transition into flame during any part of this test. And again, if this happens, the room is cleared of smoke, the air is recycled, and the test will be reconducted. Now, there are 4 criteria for compliance with cooking nuisance testing. The first is that the smoke build rate must be in accordance with the beam and mic smoke profiles. The second criteria for acceptance is carbon monoxide level shall not exceed 4.72 parts per million at 1.5% obscuration. Now, the third one is that all 4 smoke alarms in the fire test room must not activate prior to the 1.5% smoke obscuration limit. So this test is a little different than the foam tests. Remember, the polyurethane foam test required 5 samples, 3 on the ceiling and 1 on each wall. The cooking nuisance test actually requires 4 samples, all of which are mounted on the ceiling facing the broiler. And if any one of those 4 alarm activates before the room reaches 1.5% obscuration, it's considered non-compliant. And the last criteria is that the hamburger cannot transition into flame at any point during the test. Okay, next slide, please. Now you can see a picture of the actual range itself that's used in the UL fire test room. The range itself must be elevated off from the floor to reach 60.5 inches from the ceiling. Now this is done to increase the repeatability of these tests, as these particulates tend to move across the ceiling when they're heated. 2 frozen hamburgers are to be placed in the center of a broiler tray in the middle of the baking rack inside the oven. An opening of 4.5 inches from the inside of the oven door and the front surface of the oven must be maintained during this test. So the door is in a fixed open position to allow the particulates to escape the broiler freely without obstruction to enter into the room. All right, next slide, please. Now here I've captured a list of the unique smoke signatures for each of the 3 tests that we discussed today. Beginning with the flaming PU foam, which produces the smallest particle at around 0.05 microns. The particles are black in color, and they produce a thick, dense smoke plume. The smoldering foam produces a medium-sized particle at approximately 0.09 microns and is brownish gold in color, with a medium to heavy smoke plume. The cooking nuisance resistance tests begin with smaller particles around 0.06 microns, and then as the build progresses, the particles become larger to approximately 0.09 microns. Now the color is light gray, and it has to have a MIC response of 59 to 49. And yeah, in case you're wondering, this hamburger test smells absolutely awesome when it's conducted, especially when you're working late at night there. All right, next slide, please. Okay, now that we've examined all the criteria and we all have a much better understanding of these 3 new smoke detection requirements, it should be a really simple task for manufacturers to comply with these requirements, right? Well, let's look into a few of the challenges that manufacturers are facing when they're designing products to comply with these requirements. Now, the conventional technology, which is the current ionization and photoelectric technology that's available in the marketplace today, will absolutely not pass any of these new requirements. This means that the entire detection industry, both smoke alarm and smoke detector manufacturers, will need to redesign all of the currently listed initiation devices. Now, this is a very large and extremely time-consuming task. Following a complete redesign, these new products have to be listed to these new latest editions of the standard. The 8th edition of 217, as I mentioned before, has over 400 plus changes from the 7th edition. And all of these changes, as well as the ones we spoke about today, will need to be met with compliant results before a new listing will be granted. The entire process from a new design concept to a fully listed product typically takes about 3 years. However, with the current massive backlog at the certification labs caused by every single manufacturer having to list every single model of initiation devices for use, products are forced to sit in the queue for extended periods of time. This process, coupled with the COVID pandemic, is proven to take a much longer period of time than previously anticipated. Now we're going to take a look into the compliance dates and how they've been shifted in an effort to assist to relieve some of these complications in the next slide. Now, smarter detection will also be required. Smoke alarm manufacturers will not only need to design initiation devices which will identify new and very different smoke signatures such as colors and particulate sizes. Could you back up just a minute, Shane? I'm sorry, I'm not quite done with that slide. Thank you, sir. Since conventional and single source technology will not be able to handle this task, manufacturers will most likely look towards multi-criteria based approach. What is a multi-criteria alarm or detector? That's when more than one sensor is used to assist in determining a fire or nuisance situation. Additional sensors may include carbon monoxide or heat sensors, also different combinations of ion and photoelectric, or even different types of infrared and visible LEDs can all produce more information about specific smoke signatures. Now, the cost will most certainly be a challenge for all manufacturers, as the cost of these new products will inherently be driven up by more complex designs and the use of additional sensing technologies. Manufacturers will certainly be challenged to keep the price points affordable as well as complying with the new requirements. Now, in addition, narrow production limits are a very big issue. We looked at the requirement for cooking nuisance resistance, and we learned that alarms and detectors are not allowed to activate before 1.5% obscuration from the broiling hamburger, yet they absolutely must alarm prior to the 5% obscuration during the fast flaming polyurethane foam. This leaves a very narrow window in which to calibrate smoke sensitivity for these devices in production. If an alarm or detector is calibrated too sensitive, it will activate before the 1.5% limit. And conversely, if an alarm is calibrated too sensitive to meet the 1.5% limit, it may not alarm in time for the 5% flaming requirement. Now, the last issue to contend with as a challenge to manufacturers is the compliance date in which alarms and detectors must be listed by. It's very quickly approaching. We're going to take a look at the NRDL compliance dates and how they align with the requirements found in 72 in the next slide. Okay, next slide, please. Now, this is kind of an eye chart here, so I apologize for that, but there are some very important factors in this presentation on this slide that we need to look at. So May 29 of 2020 was the official effectivity date for all smoke alarms to comply with the 8th edition of 217 and all smoke detectors to comply with the 7th edition of 268. However, this past December, UL decided to extend the effective date from May 29 of 2020 until June 30 of 2021. Now, we'll talk about the reason UL did that in a few moments, but both of these standards have the same effectivity date of June 30, 2021. So why is this date significant, and what does it actually mean? It means that on that date, all of the alarms and detectors currently listed to the previous edition of 217 and 268 will no longer comply, and the product listing card will be withdrawn from UL on that date. It also means that if a manufacturer produces a smoke alarm or smoke detector after June 30 of 2021, that it must be listed to the new editions shown on your screen. Incidentally, ETL, also known as Intertek, is also an ANSI nationally recognized testing laboratory, credited with the authority to test, list, and certify products to 217 and 268. And each NRDL has the authority to choose their own individual compliance date. Excuse me just a second. Sorry about that. So even though UL has selected June 30 of 2021, ETL has chosen December 31 of 2021, about 6 months later. We can also see on the slide that the 2016 and 2019 editions of NFPA 72 had previously chosen a required installation date of January 1 of 2022. However, a few months ago at the NFPA 72 second draft meetings, NFPA decided to extend the required installation date to May 1 of 2022. Now we have to keep in mind that there are differences between the UL standards and the NFPA code. The UL standards are developed for product listings, and the NFPA codes are developed for the product installations. So why doesn't the effective date for installation codes and listing standards align with each other? Well, the answer is pretty simple. The new edition of 217 was published in the fall of 2015, and 268 was published in the spring of 2016. Shortly after that published date in April of 2016, UL released the official effectivity date of May 29, 2020. At that time, UL set out to build a completely new state-of-the-art fire test room in which to test alarms and detectors to these new requirements. As NFPA 72 first draft meetings were coming to a close, UL had not completed that new facility, and manufacturer needed a minimum of 3 years in which to develop, test, and list new smoke alarms and detectors. Now, Chapter 29 of the Technical Committee of 72 originally decided upon January 1 of 2022 to both allow UL enough time to complete their facility and also allow manufacturers ample time to develop, test, and list new products. Now, NFPA's new date of May 1, 2022 extends a few months past UL and ETL's compliance dates, and this was done to provide a generous window to purge the warehouses and distributor shelves of alarms and detectors that are manufactured before June 30th, 2021. This means products that are manufactured before June 30th, 2021 will be able to be installed in accordance with 72 until the deadline date of May 1 of 2022. So to simply recap, UL's effective date is June 30th, 2021. ETL's effective date is December 31 of 2021, and NFPA's effective date is May 1 of 2022. Now, this would be a great opportunity to have a real quick discussion regarding installation devices, codes, standards, and compliance dates, and what this all really means. I get a lot of questions from AHJs and interested parties regarding what to do with the products that are previously installed in these occupancies after the new compliance dates take effect. Questions such as, well, should all UL smoke detection be removed from service after June 30 of 2021? Or should they be removed and replaced with new products after the NFPA effective date of May 1, 2022? Or are all the previously installed devices no longer operational after the new effective date? So my response to all this is simply this. There is no code in NFPA 72 that requires existing smoke detection to be removed from service and to replace these models with listed products to the newer editions of these standards. The smoke detection requirements in 72 referencing the new compliance dates cover new occupancies only and not existing ones. So as new buildings are being built, of course, they're going to have the requirement to have the new products in those buildings after the effectivity date. Now, the only requirement in NFPA 72 to replace smoke alarms is, of course, the 10-year replacement, which is required in Chapter 29. Now, that being said, certainly there are benefits to installing smarter smoke detection devices complying with the new editions of the standards, and many of these benefits extend well beyond those mentioned in this presentation, such as transient suppression, drift compensation, hush features, and that. Now, so it's a good general practice to replace existing smoke detection? Yes, absolutely. However, is it required by NFPA 72 code? No, it's not. All right, next slide, please. All right, this map at the time of publishing kind of helps to indicate the individual states that are following 4 different editions of NFPA 72, 2019, 2016, 2013, and 2010. It also depicts that all the states do not follow the same edition. Incidentally, I tried to update this map and get the current version from NFPA. However, NFPA changed their format and they discontinued this illustration, so I can't update it. But the main takeaway from this slide is that states individually adopt the 2016 and 2019, as well as the upcoming 2021 editions of 72. They will be required to install a UL listed smoke alarm and or smoke detector that are manufactured before June 30th, 2021 until the May 1, 2022 deadline. And also all ETL listed smoke alarms and smoke detectors that were manufactured before December 31 of 2021 must be installed in the field before May 1 of 2022. All right, next slide. Oh, fantastic. That looks like our last slide. So I'd like to thank you again for allowing Shane and I to do this presentation with you today. And with that, I'd like to turn the webinar back over to Josh for a few closing words.
Thanks, Dave.
Absolutely.
So my name is Josh Gilland. I'm the project registration manager for ADI. Just wanted to pop in and say a few words and let everybody know that it is a feature that ADI offers and kind of give you a rundown on how it works. Project registration is something that most of our vendors offer. It'll come into play when you have a large project. So when we say large project, we're talking 5, 10, 15, $20,000 or more in a single location. You're working on a school, an office building, a military base, that kind of thing. Most of our vendors will offer discounted pricing for the duration of that project. My team handles reaching out to the vendors on your behalf and getting that special pricing and getting it back to you. So all you guys need to do is reach out to your local ADI sales branch, say, hey, I'm looking at doing an installation at this school or wherever it may be. This is the bill of materials I'm looking at. These are the vendors I'm looking at. Can you see about getting me special pricing? They bring it to us. We deal with the vendors. If they approve special pricing, we build it into the quote for you and get it back to you. The whole thing usually takes anywhere from 2 to 4 days. And can save a significant amount of money in the long run on this. Details you'll have to provide will have to be the end user, the location, the time frame you're looking to purchase. Sometimes they'll need some technical specs and maybe even technical drawings, things like that. It just depends on the vendor. But you just provide that to your sales rep at the branch, and we take care of the rest. It's pretty straightforward. It's pretty simple, and it can save everybody a lot of money.